Hi everyone, my name is Sanjay Chouhan and welcome to my YouTube channel. In this NLP series, currently we are discussing deep learning for NLP. And in deep learning for NLP, we have discussed RNN and LSTM. And now it's time to implement them in a real life project. So we'll be working on a case study, and this is the second case study. And in this case study, we'll be doing a spam classification. We have SMSs and we'll be classifying the SMSs into spam and not spam category. So this is the dataset we are using, which is from Kaggle. The dataset is SMS spam collection dataset. And you'll see the dataset has these columns V1 and V2. And in V1, we have the classes spam and ham. Ham means not spam. And in the V2, we have the SMSs. These are the text messages. So let's look into the notebook. So you can create the notebook for this dataset by clicking on this code, and you can just click on this create a notebook. This will create a notebook, Jupyter notebook for you to work on Kaggle using this dataset. Before proceeding with the case study, let's look into a few concepts of deep learning, which will be necessary for this case study. And actually, I created the whole video of this case study, and later I was not happy with the result because I thought that the video is not fair to the people who are not familiar with the deep learning concepts. So because they won't be able to understand a lot from the video. So I want to explain few concepts from the deep learning which are required in this case study so that everybody can benefit from this case study. We have seen this neural network architecture before. We have the input layer, we have the hidden layers. So there are two hidden layer 1 and hidden layer 2, and there is the output layer. And there are connections between all the neurons, the hidden layers and the output layers. And also there is connection between the input and the hidden layers. So these are all connections, and all connections will have some weights, right? Here we are having 3 plus 3 connection, that is 9 connections, and all of them will have some weights. And here we are having 3 cross 2 connections, and we'll have 6 different weights here. So those are represented with weight matrix as mentioned at the bottom here. In neural networks, the inputs are given and the model architecture is predefined. It's predefined before the training. So before training itself, we need to define the model architecture. We need to define how many layers will be there in the model and how many neurons will be present in each of the layers and what activation functions will be present for each of the neurons. So those all details are present before training the model. So only things that's get updated while training the model is the weights. So weights are the thing that the model will learn while training. So weights are updated in such a way that we are getting a good output from the model. So how do we know we are getting a good output from the model? We do comparison between the output that we are getting, that is the predicted output, and the actual output, that is the output that we should be getting. So we do a comparison. So we'll look into this, like how we do the comparison. First, for binary classification, the output layer will have one neuron, and the neuron will be sigmoid neuron because sigmoid will produce output between 0 and 1. But the values will be a real number. That means it will be 0.5, 0.2, 0.9. So it's not going to be 0 or 1. It's going to be some decimal number. And what we do is we use a cutoff like 0.5. So if the value is greater than equals to 0.5, then the output is 1. If it is less than 0.5, then the output is 0. That's how we classify the output y hat. So y hat is going to be a decimal number between 0 and 1 for binary class classification. And this neuron will be sigmoid neuron. And in this output layer, we are going to have only one neuron for binary class classification. Now that we have the probability y hat, we'll see how we compare the y hat with the actual output y. So for binary class classification, we have this binary cross entropy. So this is a formula for binary cross entropy. The binary cross entropy will take two parameters, y and y hat. That is the true level or actual output, and y hat is the predicted probability. And so y is going to be always either 0 or 1. So it can't be anything other than 0 or 1. So it can't be like -1 or n1. It's always going to be 0 or 1. So for our data set also, we'll convert the output levels into 0 and 1. And the y hat, that is the predicted probability, is going to be in between 0 and 1. So this will be a real number. That means this will be a decimal number. It can be ranging from 0 to 1, including 0 and 1. So it's a probability value. And this is our formula for binary cross entropy. The binary cross entropy or the functions which are used to calculate the difference between the predicted and the actual output are called loss functions because those functions calculate loss, right? That we are calculating the difference between the actual and the predicted output. So there is a loss. So we are calculating the loss. That's why these are called loss functions. So each of the output will be either be 0 or 1. And for each of the output, only one of the term from this formula will be active. So let's look into this. So if y is equals to 1, that means if the actual output is equals to 1, then the binary cross entropy will be like this. It will be minus log of y hat. And if y is equals to 0, then the binary cross entropy will be minus log of 1 minus y hat. So the formula will be reduced to this based on the actual output. So this is the calculation for one input or one output. But in reality, in the training data set, we'll have multiple inputs. So for multiple inputs, we take an average. So this is the binary cross entropy formula that we saw, right? And if we have like n number of samples, then we take an average over the samples. So this is the averaging of the whole function. So let's understand the binary cross entropy formula with some examples. So we have two classes, positive plus and negative plus. So if y is equals to 1, that means positive plus. So if y is equals to 1 and the prediction that we are getting is 0.9, that means it's a correct prediction, right? Because if we use the cutoff of 0.5, then it will be 1. This will become 1. So it's a correct prediction. So the formula, we have put all the values into the formula, we'll get output of 0.105, which is a low number. That means the loss is low. That's understandable because the prediction is correct. And what if the prediction is wrong? That means here we are having a y hat of 0.1. That means this is a wrong prediction because it's near to 0. This prediction is near to 0 and actual output is 1. So if you put all these values here, you'll get a 2.302. That means the loss is high, right? That means a bad prediction. Now let's look into the second case. If y equals to 0, that means if it is a negative class and we are predicting correctly. So if y equals to 0 and y hat is 0.1, that means the actual output is 0 and we have predicted 0.1. So which is near to 0. So that means it's a correct prediction. And if you put all these values in this formula, you'll get 0.105, which is a low number. That means the loss is low. And if the loss is low, that means a good prediction. And let's look into the second part where the prediction is wrong. So y equals to 0 and y hat is 0.9, which is near to 1. That means this is a wrong prediction. And if you put all of this, you'll get 0.302. That means this loss is higher. High loss, that means bad prediction. So the BC is calculating the loss. If the output is near, the predicted output is near to the actual output, then the loss is low. And if the predicted output is far from the actual output, then the loss is high. And we want to minimize the loss so that the actual output and the predicted output are aligned. So in training, we try to minimize the loss. To minimize the loss, we need to update the weights. So in gradient descent is a technique with which we update the weights step by step. So by step, I mean that we send few data points, batch of few data points to the neural network layer, get the average loss, and then update the weight. So let's suppose we have 1,000 data points in our training examples, and we can take a batch of size 50, then we'll have 20 batches, right? So we are having 1,000 data points, we are batching them into 50, then we'll have 20 such batches, and we'll send one batch at a time. We send the one batch through the neural network, get the average loss, and after the loss calculation, we update the weight, then send the next batch, again calculate the loss, and then update the weight so that the loss is minimized. And for weight updation, we use this gradient descent technique, and this is the formula for gradient descent. W is the new weight equals to old weight. This is W minus old weight minus eta into partial derivative of the loss function with respect to weights. So these are the components of this function: weights, learning rate, loss function. Here the loss function is the binary cross entropy, and gradient of loss function with respect to weight. The gradient of binary cross entropy with respect to the weight is this. So partial derivative of loss function with respect to weight is y hat minus y into x. X is the input. So this is what we get when we do this partial derivation of the loss function. So in using this formula, we'll keep updating the weights one batch at a time, and we'll keep doing it till we reach a point where we can't minimize the loss anymore. And we'll reach a optimal weight, and that optimal weight will be used in the model for future predictions. So let's look into another concept called dropout, which is a technique for reducing the overfitting of the neural network. So it's used in training to reduce the overfitting of the model so that we do not rely on a connection uh, too much. So this reduces reliability on a particular connection of. Let's suppose there is a dropout between these two hidden layers. Okay, so this is hidden layer one, and this is hidden layer two, and in between we are doing dropout. So when we do dropout, there is a percentage we need to mention. 0 to 100 are like typically like 20, 30, 50. So let's suppose here we are having a dropout of 33. So here we have six connections, right? 2 into 3, 6 connection. And if you are mentioning the dropout of 33, that means if you take 33% of 6, it's going to be 2. So in training, at each step, we will remove 2 connections. So it will be something like that. Here we are removing 2 connections, right? Only 4 will be there. In the next batch, when we pass the next batch, we'll remove another 2 connections. And like here, we have removed 2 more connections. And we'll keep doing this for each batch until we have trained the model. So it reduces the overfitting issue by not relying too much on a particular connection, a particular set of connection, because in dropout we might remove the connection and then we need to update the weights, ignoring those connections. That's how the dropout helps in reducing the effect of overfitting. So in this notebook, we'll have the CSV file for the dataset. So this is the dataset we have. It's spam.csv at this location. Okay. So first, we are importing various libraries. First one is the pandas, and then the sklearn. From here, we are importing the trend test split function. And from TensorFlow, we are importing various modules for LSTM and trainings. And we'll see how these are used later in this video. So let's first import them. Now we'll load the dataset using pandas from this location. And you see, this is the first 5 rows from the dataset. We have this V1, V2 column, and there are three more unnecessary columns which we'll ignore. In the V1, we have the labels or the output, M and spam. M means not spam, and then this is spam. And in the V2, we have the text messages. So first we need to create the dataset. Basically, first we need to prettify the dataset. So we'll rename the V1 and V2 category columns. So V1 is renamed to label, V2 is renamed to text. And we'll also convert these labels or the outputs into numeric form because we need to convert them for model training. So we'll convert ham to 0 and spam to 1. So here we are mapping ham to 0, okay, and spam to 1. So wherever we are having ham, it will be replaced with 0, and wherever we are having spam, it will be replaced with 1. So let's run this, and there's something wrong. Let's redone. And let's look into the head of this new data frame. So this is the new data frame. We're having label and text. Label are zeros and 1. 0 is the spam, not spam, and 1 is the spam. Okay, and these are text messages. Let's look into the distribution of the data points. So we have 4,825 not spams and 747 spams. So the difference between spam and not spam is huge. Because only 13% of the data points are spam and remaining 87% are not spam. And this is the scenario for a data imbalance, which is not good for model training. So we need to balance the data set somehow. And one of the technique for balancing the data set is undersampling. So basically, we'll discard the data points from the majority class. So majority class is not spam. So we are having more data points in this not spam category. So from this, we'll discard few data points and select only few data points to build a new data frame. So here we are creating a data frame one where uh, which are not spam, and we are sampling 1500 data points from this not spam category, and we are taking all the data points from the spam category. So let's run this and let's create the new data frame. So this is the new data frame. We are concatenating df1 and df2, and we are just taking a sample just to randomize the data points. And so then, sorry, we need, so I have run this, need to run this again. Okay, so we have now we have 2247 data points. Okay, we have reduced the data points. Let's see the ratio again. Now we have 1500 data points from not spam category and 747 data points from the spam category. Now this difference is not much. We are having around 33% data points in not sorry in spam category. Now the ratio is slightly balanced, so we can do the training with this data set. So the first step for this model building is the tokenization. We need to tokenize the data set. So we'll be using this tokenizer, which is from TensorFlow. And let's look into the tokenizer. So in the tokenizer class, we are passing num words equals to 5000. Basically, we are saying that this tokenizer will have total number of 5000 distinct words. So that means the vocabulary size will be 5000 and not more. And we are passing the text, data frame text column. So we are calling this fit on text. So this will create the vocabulary. And so basically what it will do is it will it will count the frequency of each of the words, and whichever the words are having higher frequency will be retained and others will be discarded. So only 5,000 5,000 words will be used and remainings will be discarded. So the vocabulary size is 5,000, which we have mentioned in this tokenizer class. So once this is done, it will basically it will create a mapping of words and the number. So each of the 5,000 words will be mapped to a number from starting from 1. So we'll look into the mapping later. Let's first run this next. Let's first run this cell and then we'll run this cell. So here what we are doing is that once we have created the vocabulary and the mapping, we can convert this text into sequence. So we'll pass this df text column. We are passing this column and we'll get a sequence. So it will be numeric representation of the whole text. The length of this sequence is going to be same as that length of the data point, that is 2247. And if you see length of this first sequence, that is sequences 0, is 28, and length of the third one is 7. So what are these 28 and 7, right? So to understand this, let's view the data point at the third location. So we are printing that text at the location, third location. So the text is, okay, I asked for money, how far? This is the text, right? Here you see that we have 7 words. Okay, I asked for, and so on. So this is the number we are seeing here. Basically, this is converted into a vector of size 7. Okay, let's print this to see. So this is converted in this list format. For each of the word, we are having a number. Each of the words are mapped to a number. And these are present in the tokenizer. So if you see tokenizer word index, so for the word okay, the index is 68. So that's why here you see 68, because we are seeing okay at the starting. And for the word I, the index is 3. So you're seeing the 3 in the second cell of this array, right? That means each of the words are tokenized and each of them are mapped to a number. And number will be ranging from 0 to 5,000. Sorry, 1 to 5,000. This is how tokenization happens. So for LSTM or RNN, basically in deep learning, we don't need to do traditional text pre-processing, which we have done in the previous case study, because those are not necessary in case of deep learning. And also the tokenizer is doing some kind of pre-processing. So here's we are filtering out these symbols, these punctuation marks and some other symbols. And it's also converting the text into lowercase. So these two things are done. And we are splitting the text based on white space. So these three things are done automatically by this tokenizer. And we don't need to do any manual text preprocessing in case of deep learning kind of techniques. Now we need to do padding or truncating. So basically what we do is, we see here that we are having the sequence of different length, because messages are of different length. So the representations are also of different length. So here we are having, for the first one, we are having length 28. And for the fourth one, we are having length 7, right? So this is of different length. But for LSTM, we need to have the sequences of same length. That means for each of the data point, the length should be of same size. So to make the length of same size, we'll use this padding function. So basically we have these pad sequences. It will convert the sequences into a same length. So to convert the sequences into a same length, if the length of the sequence is less than the desired length, then it will add zeros at the beginning. And if the length of the sequence is greater than the desired sequence, then it will truncate from the beginning. So this is the function we are calling paired sequences, and we are passing our sequences. And we are mentioning that the max length for the sequence is 100. We'll get the padded sequence. Uh, Let me run this. Now the length is 100. You'll see this is how it's modified. Basically, we have this, all right, we have seen this 68, 378. So this was for the fourth data point. So we have this at the end, and before this, we have added zeros. So it will prepend zeros and make the length of this representation of size 100. So now each of the data points will be of size 100. So the size is 100. Now we are ready for the model building. And before model building, we need to create our train, test, and validation split. So we are using this train test split function, which you have already seen earlier. So I'll run this and we'll see the split sizes. So in the training, we are having 1347 samples. In the validation, we are having 450 samples. In the test, we are having 450 samples. Let's look into the model. So this is the model. This is the model which we are building. The first thing is sequential. This is a class where we'll pass all the layers. So sequential means the layers are in sequence. We have one layer after the other. So you remember we discussed that LSTM, and then before LSTM we have this embedding layer, right? So the first layer is the embedding layer. This is the embedding layer. Next is the LSTM layer. Next we have the dropout layer, and this is used for reducing the chances of overfitting or reducing the effect of overfitting. You can ignore this if you want, but this is required so that the model doesn't overfit on the training data and it won't be able to perform on the unseen data. So this is needed. And then we have dense layer. Okay, so we have one layer after the other. That's why it's sequential. And the first one is the embedding layer. So look into the embedding layer. In the embedding layer, we have three parameters: input dimension, output dimension, and then the input length. We're saying input dimension is 5,000 because this is the vocabulary size mentioned in the tokenizer, right? So in the tokenizer, we have mentioned the vocabulary size to be of 5,000. So we need to mention that input dimension is going to be of 5,000. And the output dimension is 100. This is output representation for each of the sequence or each of the data points. So we'll get for each of the data points or each of the text messages, we'll get a vector representation of size 100. And input length is 100. That means our sequence length that we are providing is 100. So our padded sequence is of length 100 that we have created, right? So that's what we need to mention in the input length. Next thing is the LSTM. So in an LSTM, we have this 64. 64 is the number of cells in the LSTM. Basically, you can think of this as size of the hidden state vector. So the hidden state vector or the cell state vector or the output vector will be of size 64. And we are mentioning return sequences equals to false. We have seen that LSTM can output at every time step. And we can use output from each of the time step, or we can take the output from the last time step and use it. And in some cases, taking the output from each time step is useful, but in most of the cases, you can take the output from the last time step because it will contain all the information from the sequence. So here we are saying that return sequences equals to false. That means it won't say return all the sequences. It will only return the sequence or the output from the last time step. Next one is dropout. This is as I mentioned, this is for reducing the overfitting. And next one is the dense. So dense is a under layer. This is for output. This is the output layer. So in the output layer, we are having one neuron, and the activation function for this neuron is sigmoid. Why are we using sigmoid? We are using sigmoid because sigmoid will provide output between 0 and 1, right? It will convert anything into 0 and 1. So this will give us a probability of spam class. That means If the value is near to 0, then it's probably a not a spam. And if the value is near to 1, then it's going to be spam. So we'll have a cutoff at around 0.5. So if the probability is greater than equals to 0.5, then we will say that it's a spam. Otherwise, we'll say it's a not a spam. So that's why we are using this sigmoid neuron at this last layer, that's the output layer. And we only need one value from this last layer, right? We only need the probability value. So that's why we're using only one neuron. And dense means we'll be having all the connections. So this is the model. This is a sequential model with these layers. So we have created the model. Let me run this cell. Okay, I'm not sure why it's saying. Okay, so we have created this LSTM model. Okay, here is the LSTM layer. Now we need to compile. So while when we compile, it will configure the model. So in compile, we are passing three parameter, right? One is the optimizer, and second one is loss, and then matrix. So optimizer is mostly going to be Adam for most of the neural network models because this is most common optimizer and most advanced optimizer. The optimizer is used for regulating the learning rate. And the loss function is used for calculating the loss or the calculating the difference between the predicted value and the actual output, and then updating the weights of the neural network. So here we are having binary classification. So our loss function is binary cross-entropy. The matrix parameter is used for monitoring. So we'll be monitoring the accuracy while training. If you're not knowing this, if you don't know this optimizer loss, that's fine. You can use these parameters. Basically, optimizer and loss are used for training the model. These determine how the model is trained and how the weights are updated. So we may know the model training happens in steps, right? We have some input data, we pass through the neural network model, we'll get some output, and we'll compare the predicted output and the actual output. And for comparison, we'll be using loss function like this. And then based on this loss, based on the differences, we'll be updating the weights. So I had mentioned earlier in the neural network basics video that the initial weights are random and we learn the weights as we train the model. Next thing is training the model. So we'll call this fit function model.fit. And in this fit function, we need to provide the training data. So xtrain and ytrain. Xtrain is the input data and ytrain is the output data. And we have this parameter epochs, batch size, validation data. So validation data is the xval and yval. So these are used for monitoring the performance so that we know that how the model is performing. So after each epoch, we get the validation accuracy. We mentioned that matrix is accuracy, right? So that you can monitor the progress of the training. So the model training in neural network will happen step by step. We'll pass some data points through the model, right? And then we'll update the weights. So batch size is like how many data points we are passing to update the weights. So we'll first pass 32 data points and then we'll update the weights based on the loss. Then again we'll pass next 32 data points and we'll update the weights. So batch size is like how many data points we are passing. We can pass the whole data point or we can pass many batch size like 32, 64. So we are passing 32 data points and epoch is how many times we are using the training data. So if you pass 32 data points and if you run out of the whole training data, that means we have run for one epoch. Then you can start again at the beginning and start again at batch one. And then if you pass through the whole training data again, then the epoch is two. So here we have mentioned epoch is three. That means we will be passing through the whole training data thrice. So let me run this. So this is the first epoch, epoch 1/3. And you see that this is 43. 43 is the batch, total number of batches. And why 43? So the training is already done, right? So let me see. So in the training, we had 1347 data point, right? and we have mentioned the batch size as 32. So if you create a batch of 32, we'll have 43 batches for this training dataset. That's why you see 43. So in the epoch 1, we are passing through all the 43 batches. Then we again pass through in the epoch 2, we are passing through the 43 batches again. So one epoch means passing through the whole training data once. And batch size is for updating the weights, aging the batch. So here we have lots of things to unpack. We know epoch, we know batch. We have accuracy. So this is the training accuracy, and this is loss, training loss. And this is for the first epoch. Okay, this is the first epoch training loss and accuracy. And this is the validation accuracy and validation loss. In the next epoch, the accuracy improves. So it's going from 72 to 96%. And in the next epoch, in the third epoch, it's going to 98%. So the training accuracy is improving in this epoch by epoch. And similarly, the validation accuracy also is improving. So it's going from 95 to 97. And in the third epoch, it's not going up, it's staying around at 97. However, the validation loss is improving, it's decreasing in each epoch. So now we have trained the model. So now we have the LSTM model. So let's look into the performance. This is the performance for the train and the validation data, but the actual performance will be measured from the test data, right? So let's evaluate on the test data. So we'll be running this cell. Here we are evaluating the model on this test data. We're getting an accuracy of 96%, so which is very good, right? We are getting for the validation, we are getting 97% accuracy, and for the test, we're getting accuracy of 96. So it's a very good model. So it ran quickly, right? But if we are using very large data set, or if we are having more number of layers, then it might take some time, and you'll need to monitor these things like train accuracy, validation accuracy to see if the model is improving and if the difference between these two accuracies, right, train and validation accuracies, is minimal. If it is huge, the train accuracy is very high and the validation accuracy is very low, then the model is overfitting. Then the model is only performing good on the training data, but on unseen data, it is not performing well. So you need to monitor those things while training. Okay, so now that we have trained the LSTM, let's look into the model. So we can get the details of the model using this model summary. So this will give us the various details from this model. So we had this layer, right? The embedding layer. We have this LSTM layer and dropout and then dense layer. We have this shape of output. This is the output shape and number of parameters. How many parameters we have in each layer. So in the embedding layer, we are having 500,000 parameters. In the LSTM layer, we are having around 42,000 parameters. And at the dense layer, we are having 65 parameters. So why 65? Because vector, the output vector is of 64, because we have mentioned 64 in the LSTM unit, right? So 64 plus 1 for bias. So that's why we're having 65. So all of them will be connected to one single neuron. So that's why we'll have 65 weights. In total, we are having around 1.6 million parameters. And out of this, around 542,000 are trainable parameters. So these will be trained. You can also plot the diagram here. Basically, this is same thing or similar thing. Here we are having the layers and then the input and output shape of each of the layers. Now we'll see RNN. And RNN will be very similar to LSTM. The code will be very similar. Only this one line change will be there. So let's open at the code. We'll start from the model building. We are building the RNN model here. And the same thing is there, right? We are having the embedding layer, dropout layer, dense layer. And instead of LSTM layer, we are having simple RNN layer. Here also we are mentioning 64. It with the size of the hidden state vector. And return sequences will be false because we'll be using the output from the last time step. And we are comparing the model as before. We are using the same atom divisor and the same loss function, which is binary cross entropy. So let's run this. Okay, clearly. Now we will be training the model by calling this fit function. We are providing the same train data, S size, epoch, validation data. So the code is same. Only the changes in the code is this layer. Only this line is changed. Everything will remain same. So we are calling this fit function. Will be running for 3 epochs, right? At each of the best, we are updating the weight. So here also we are having this train accuracy, train loss, validation accuracy, and validation loss. We are able to achieve the train accuracy of 97 and validation accuracy of 98. And let's see the performance on the test data. On the test data, we are seeing accuracy of 95.56%. So which is a very good number. So for both the LSTM and RNN, we are getting a good performance. Here we are getting 96.22 for LSTM and 95.56 for RNN. Now that we have seen for RNN and LSTM, you can also try out bidirectional RNN from your end or GRU. So the code changes will be very minor from this. You can try out all those different models from deep learning. And LSTM and RNN are mostly used for time series data where we have sequence of data. Like we can have weather, right? We can have temperature at every hour, and we can use the temperature from every hour to predict the temperature of future. And like demand forecasting is also an example of time series. So we can have hourly demand for cabs, particular location like Delhi. And what we can do is based on all the previous demand, we can have like last 1 week of data feed into the LSTM. Then we'll be able to predict the future demand. So these are also used in time series data and NLP data because there is a information, sequential information. Thanks for watching. I hope this was very helpful. If you have any queries, please comment and let's see you in the next video. Bye.